Okay, folks, so I can see we're just about to hit 1 minute after the hour, so we're going to go ahead and get things started. My name is Matt Thomas, and thank you for tuning in to the USGS Landslide Hazards Seminar. This meeting is hosted by the USGS Landslide Hazards Program and co-organized with contributions from Stephen Slaughter and Jamie Kostelnik. For those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone or video camera. We're going to wait until the end of today's presentation to take questions. So in the meantime, please just do your best to make sure your microphone is muted and your video camera is off when you're not intending to speak. It's my pleasure today to introduce our speaker, Dr. Pukar Amatia. He is an associate research scientist with the University of Maryland, Baltimore County, working at the Hydrologic Sciences Laboratory, NASA Goddard Flight Space Center. He's a member of the NASA GSFSC Landslides team. And his primary responsibility is to develop open source landslide mapping systems to rapidly map landslides, supporting disaster response activities, and generating inventories to train the global landslide hazard modeling effort undertaken by his team. He's also focusing on exploring deep learning frameworks for mapping landslides using optical and SAR imagery. He received his PhD in atmospheric physics and atmospheric environment from the Institute of Tibetan Plateau Research, Chinese Academy of Sciences in 2016, and his master's degree from the Faculty of Geoinformation Science and Earth Observation at the University of Twente. The Netherlands in water resources and environmental management. Pukar received his BE in civil engineering from the Institute of Engineering in Nepal. So Pukar, thank you so much for taking the time to speak with us today. I'm going to go ahead and turn it over to you.
Yeah, sure. Thanks, Matt, for the introduction. So I'll just skip introducing me and just get straight to the presentation. So today I'm going to talk about introduce various rapid response landslide mapping open source tools and our effort quantifying accuracy using the 2021 Haiti earthquake as a case study. So I'm going to divide this talk into two parts. For the first part, I'll just be talking briefly about my research and the background under which this study was undertaken. And for the second part, I'll be talking about the rapid response efforts and some things to consider in future. So let me just start with providing a brief introduction of my research team. So I'm a member of the NASA GSFC Landslide team, where we map and model landslides at different scales. So at local scales, we develop landslide mapping systems. At regional scales, we develop models to map susceptibility. And at global scale, our landslide hazard assessment for situational awareness LASA model provides near real-time assessment of landslide hazards worldwide using satellite precipitation. So if you're interested in our models or type of work I do, I encourage you to visit our websites, which is landslides.nasa.gov. So within the team, my primary responsibility is to look at development of open source tools to rapidly map landslides using optical or SAR imagery. So in terms of remote sensing of landslides, there's basically two ways we can do it. One is pixel-based and another one is object-based image analysis. So in pixel-based, spectral information of single pixels are used to identify landslides. And for a spatial process like landslide, that might not be ideal. And the main problem with this method is it suffers from salt and pepper effect. If you look at a classified image, you will see a lot of noise in it. So it's basically due to single pixels sometimes being demarcated as landslides. The real advantage of this is it's computationally not expensive and it can be done quickly. So another method is called object-based image analysis, or BIA. So this is one of the primary methods that we use in our teams. So instead of working with single pixels in object-based image analysis, we group homogeneous pixels to form an object. So an object in a literal sense is a polygon made out of similar pixels. And then for the classification process, we use various spectral, textural, morphological, geometrical, and contextual information of these objects and use machine learning to classify whether this object belongs to a landslide or non-landslide class. So one of the cons of this method is it's a little bit computationally expensive, but comparative studies between the two methods have shown that OBIA maps landslides with much higher accuracy than pixel-based methods. So object-based image analysis basically consists of two steps. The first one is segmentation, the process of grouping similar pixels to objects. So you can use various kind of segmentation algorithms such as multi-resolution segmentation, mean shift segmentation, etc., to group pixel into an object. So here in the image, you will see what an object looks like. So it's basically like grouping similar pixels to form small polygons, which we can use to map landslides. And the second step is like taking those objects and classifying it, whether it belongs to a landslides or non-landslide class. So there's technically two ways you can do it. One is using a rule set based method where a human interpreter basically sets rules on how to classify an object to landslides, or you can use machine learning techniques such as random forest and support vector machine. So back in the day, in 2017, when I was just starting, like most of the systems that could do object-based image analysis was based on commercial softwares. So one of the objectives we had was to create an open source landslide detection system, which can be easily deployable and map landslides with reasonable accuracy. So we had certain goals on why we wanted to do that. First one is to support rapid response efforts here at NASA. The second is to provide training or validation data for landslide models. And third and ultimate goal would be to release those map inventories to general public for future use as well. So the system we developed here at NASA is called Semi-Automatic Landslide Detection System. In short form, we call it SALAD. So it basically combines various open source Python packages to create a system that is capable of running in both Linux or Windows environment to map landslides. So SALAD uses object-based image analysis, as I told before. So it uses a segmentation algorithm called mean shift segmentation. And when you provide an optical imagery, so here, like we are generally using post-event imagery. I will explain the reason why later, and then a DEM. So when you provide an post-event imagery and DEM, it uses mean shift segmentation to generate objects. And then you can bring in many type of features which can be used for identifying landslides, such as NDVI, slope, brightness, etc. Then you do need, as it's a machine learning system, like you do need a handful of inventories to train the machine learning model. Here we use random forest model to predict whether that object belongs to a landslide or non-landslide class. And then at the end, we merge all the objects that belongs to landslide class to create landslide polygons. We do some visual analysis to remove or correct some of missing or misclassified landslides, and then produce a final landslide inventory. So this code is actually available publicly. So if you're interested, you can visit github.com/NASA and look for the SALAD algorithm over there. So during the development phase, we tested out this model in a small area along a highway in Nepal, where a lot of landslides were induced during the 2015 Gorkha earthquake. So in terms of validation, what we did was like we compared the landslide detected by SALAD with a manual map landslide. So in the screen, producer accuracy gives you what percentage of manual map landslide were actually identified by SALAD, and user accuracy gives you an estimate of what percentage of map things were actual landslides. So I just wanted to put out this accuracy assessment in the beginning so that we get an idea that even though automated mapping methods are very quick, it does have its own sets of challenges as well. It misses landslides and it does generate false positives. Now, there are some ways of minimizing false positives, like using slope threshold and stuff like that, but to get 100% accuracy is not possible. But what it helps in is speed, right? For example, like for the 25 by 25 kilometer tile that I mapped manually, it took me 6 hours to map it. But using a handful of landslide inventories and training the SALAD model, I was able to do it within 1 hour. So this kind of time gain is very important in rapid response scenario. In rapid response scenario, we are generally interested in identifying where landslides are. So on the bottom figure, you see a density map that we generated using the SALAD detected landslides and manually mapped landslides, and you see the general distribution is quite identical. So this might be very valuable in rapid response scenarios. So as I said before, like the first version of SALAD usually only takes in a post-event imagery, so it doesn't really have a capacity of separating old and new landslides. So in rapid response scenario, it's very important that we map new landslides only so that proper materials or like action can be taken at necessary areas. So after 2019, like NASA's commercial small sat data access program provided unlimited access to planet imagery. So our chances of getting pre-event imagery generally became better. So we introduced a change detection model to the salad. So we call it salad series. So basically, like we utilize pre and post event imagery. And instead of using a single landslide diagnostic matrix, we use change detection based matrices such as change in NDVI, principal component analysis, and independent component analysis, which is basically a dimensionality reduction technique, which highlights change. And then the rest of the model follows the same setup as salad. So what this allows us to do is like look at individual landslides that were induced during individual events. So for example, here in 2020, Hurricane Eta and Iota passed at relatively short time. So you can see like which landslides were generated by which event. So that's pretty much very valuable information in rapid response scenario. So during this same phase, we were also involved in an initiative called SHIOS Working Group Disasters Landslide Pilot. So Community of Earth Observation Satellites, SHIOS is basically a consortium of worldwide space agency with the goal of coordinating civil space-based Earth observation programs for benefits of all. Under CEOS, we have a lot of working groups, out of which disasters is one. And then under the working group disasters, you have various pilots, so the landslide pilot, fog pilot, etc., with its own goal. So our team was part of one of the pilots known as landslide pilot, so whose basic goal was to highlight the effectiveness of remote sensing and machine learning technologies to basically detect, map, and monitor landslides. So some of the landslide mapping system that I'm gonna talk about later was developed as part of this initiative, and its secondary objective was also to highlight use of Earth observation across different landslide disaster risk management scenarios. So so we had multiple leads for the CS landslide pilot. Like our team was involved. Jonathan Gott from USGS was involved as well, and then we have John Philip Malay and Sigurd Rosner from European side. So this lasted from 2017 to 2019, and then from 2019 to present, we have moved on to a demonstrator phase where we take the system that was developed during landslide pilot and then try to highlight some applications of it. So during this phase, like some of the old co-Is were replaced by new co-leads, I would say. And then in terms of applications, like we were trying to identify hazard along transportation railways and oil pipelines as a second application. We did, I think, landslide risk financing study in Morocco for the World Bank. And the third application was to generally use the systems that we developed to generate global landslide inventories to support global research, and also for this system to be used for disaster response. So in 14 August 2021, magnitude 7.2 earthquake hit Haiti, triggering thousands of landslides. And on 17 August, tropical cyclone Grace crossed Haiti, dumping more rainfall and inducing additional landslides. So during this phase, like all of the participants of the landslide demonstrator were producing results using their own system. And this was an ideal scenario where we could actually test like how this system behave in a rapid response scenario, as opposed to a development phase where we have a more lenient approach and trying various things to make it more accurate, right? So we set out with the objectives of like documenting the automated landslide rapid response products, and ultimately like quantifying accuracy so that it can be used in future to gauge like whether it's useful for rapid responders or not. So this study was published in Natural Hazards in 2023. So later in the chat, I can put a link to it. So if you need more information regarding this system, So you can visit that paper as well. So in terms of response to government agencies, 5 universities and 1 private company like responded on behalf of 3 different uh, response programs. So in terms of USGS, I think scientists from Earthquake Hazard Program and Landslide Hazard Program collaborated with USAID, USGS Landslide Disaster Assistance Team to map landslides. So the NASA Disasters Program primarily support research looking at every aspect of disasters life cycle, but it also has a mandate for responding to natural disasters when called upon or we receive a specific request from a stakeholder. So on behalf of NASA, a team comprising of our landslide team, together with University of Maryland, JPL, University of Michigan, and University of California, Berkeley, whom I'm going to refer to as NASA team going forward in the presentation, responded. So another initiative is the International Charter Space and Major Disasters. So it's just a collaboration between 16 space agencies and disaster management organization through which satellite imageries are provided to support rapid response. So the charter also can call upon their charter members' expertise to produce meaningful data using the satellite imagery that was released to support the response effort. So on behalf of the charter, the two entities responded. So the French National Center for Scientific Research, through its research organization EOST at University of Strasbourg. Moving forward, I will refer to them as CNRS EOST team, responded on behalf of the French Space Agency and on behalf of the Canadian Space Agency BGC Engineering, a Canadian geotechnical firm with expertise in geohazard and remote sensing, responded. So one difference here is like the CNRS EOS team responded right after the earthquake, and then the BGC team responded after the tropical storm Grace passed through. So here in this table, I list the rapid response products that were released during the Haiti event. I'll go through this in more detail as we move to the presentation, but the first product that was released was by USGS. So the method they utilize is a manual landslide initiation point mapping using optical sensors. So they combined various optical imagery from Maxar, Planet, and Sentinel-2. The first image for the first data were actually shared in August 16, with the final complete data released in December 7 of 2021. So the NASA team, the primary data shared was a synthetic aperture radar-based backscatter change heat maps. So they basically utilized Sentinel-1 satellites, and this data was released in August 17 of 2021. The CNRS EOS team utilized a automated landslide detection and inventory mapping algorithm they call Aladdin. So it's basically utilizes optical imagery to map landslides, and they use Maxar Planet Sentinel-2 imagery as well. They released this inventory in September 2, and there were multiple releases as well as more imageries came through. One was in October 14, and they also manually mapped landslides in polygon format across the whole affected area, and that is what we used to validate these products in March 18 of 2022. So BGC Engineering used a method or like an app called HazMapper in Google Earth Engine, which basically looks at NDVI change to map landslides, and they basically utilized Sentinel-2 based optical imageries, which release date of September 3, 2021. So all of these tools are open source, and if you want to like look at this data, they are available online as well. So I talked a lot about SALAD. So we did some mapping using SALAD. This event is pretty unique because right when the earthquake struck in August 14, there was a sentinel pass in that area. But the problem was this area was heavily cloud covered. So basically, we just did a small scale mapping where we mapped about 525 landslides. But during this time frame, we got in touch with USGS and we realized that they were launching a wide-scale landslide mapping effort using high-resolution imagery. So we didn't pursue mapping with salad further. So in terms of USGS, they released a manually mapped initiation point-based landslide inventories. So I think there was around 5,000 landslides in this inventory. So they basically utilized two methods. The first one was downloading whatever imagery was available in SGGS and manually mapping it. And second method was like using online tools provided by Maxer and Planet to map landslides as well. So this is one of the most complete and accurate inventories that exist online, as it's manually mapped, and it also provides further information on like effects to road and landslide, dam lakes, and etc. So in terms of like automated methods, generated rapid response products, which I'm going to talk about later, like they were basically three methods, as I mentioned before. Each of them offered various coverages. The SAR heat map offered the largest coverage, and then HazMapper, and then Aladdin, as it's based on a Pleiades imagery, which is very high resolution at 2 meters. It is a tasking-based satellite, so it was primarily tasked to take imageries over the Pikmakaya National Park area where majority of the landslides were. So one of the first rapid response maps that was released was by NASA, which basically utilized synthetic aperture radar-based backscatter intensity change method. So as I mentioned before, like right after the event, cloud cover was present in this area. So the advantage of SAR is that it can penetrate clouds and then can obtain imageries day and night. So it's pretty much useful in a rapid response scenario where cloud cover are present. So we basically used a approach called log ratio, or like I ratio. It's basically backscatter change pre and post event. So when a landslide happens, like it removes vegetation and stuff like that, surface properties are different pre and post landslides. So that can be exploited and used to identify areas where landslide might be possible. So synthetic aperture radar is not that handy as optical imagery as it has as it is as it has its own sets of challenges if you want to map manually. So there are also noise associated with it. So previous studies have shown that image stacking helps remove that noise to a certain extent. So what we did was like we create a pre-event stack and post-event stack and just subtract it to identify landslides. Here you see, I think, landslides that were identified in Hiroshima, Japan. So here is the sentinel imagery and then the backscatter change signals from the synthetic aperture radar. So this system that we used, developed by Handwerker et al., is implemented in Google Earth Engine. So it's available to all, and it's very easy to use. The advantage of like developing a system in Google Earth Engine is like you don't have to download and process large volume of data as we need to if we are manually processing a Sentinel-1 SAR data. So how it maps or like identify landslide is like it creates a I ratio raster. So it's basically like backscatter intensity difference between pre and post. And then we have to use a threshold to separate pixels that we think are related to change that associated with landslides. So what we do here is like we try to minimize false positives as much as possible. So we utilize the 99th percentile I ratio threshold to identify areas where change has happened. So if you look at figure number B, this is a 99th percentile I ratio detected landslides in Hokkaido, Japan. So you see, like if we share a map like this, it will be very difficult to understand what is what. So what we use is an approach where we generate or like use those I ratio thresholded pixels and generate heat maps associated with it, so that it was a little bit easier for us to visualize areas with high density of landslides. So here is a heat map that is generated in Google Earth Engine itself for Hokkaido earthquake. So for Haiti, like we utilize similar approach of Handwerker et al. And then use the log ratio change method to generate a heat map. So as I said before, like it uses event stacking, so we need to provide date ranges. So for pre-event imageries, we utilize images from August 1, 2017 to August 13, 2021. And then post-event imagery, we used a time frame from August 14 to August 16. So there was only one post-event imagery available. And we were lucky in this scenario that we had a Sentinel-1 pass right after, I think in August 15. So in general cases, that might not be a case, but we were able to identify areas where a high amount of landslides were present. So another technique, this is used by the BGC engineering team, is also based on Google Earth Engine. It's called HazMapper, and it's developed by Corey Shipp and Carl Wegman. So it's a very useful app for visualizing changes associated with landslides. So here, also like you need to give in a pre-event time frame and a post-event time frame, an event date of when the event happened, and then it will give you a visualization of where the NDVI changed. So it's basically using an NDVI differencing technique, and you can choose between Landsat 7 and 8 imagery and Sentinel-2 imagery. So HazMapper also uses image stacking technique, but instead of working with single pixel or like NDVI itself, it tries to identify maximum NDVI window stack in what is called a greenest pixel. So a greenest pixel, in a sense, is a single composite image where maximum NDVI for each individual pixel is recorded. And then we basically use a relative difference in NDVI technique to highlight areas where vegetation has changed. So here you'll see the visualization for landslides that were induced during the Haiti earthquake. So one of the things with HazMapper is it is useful for visualization, but if you want to generate inventory of polygons to do further analysis, then you need to download it and then do a thresholding as we did with the SAR density heat map as well. So here, once we have the RD-NDVI raster, that we use a threshold of -30%. So this is a threshold provided by the authors based on previous experiments that they did. So here also, you just provide event date and then duration. Pre-event duration is 2 months. Post-event duration is 2 weeks. And then you want to provide the probability of how much cloud cover you want to consider, and then also some slope thresholds to remove water bodies. So here, in the screen, you see landslides that were mapped by HazMapper. And the final rapid response technique that was used by the CNRS EOS team is called ALADIN, which full form is Automated Landslide Detection and Inventory Mapping. So it's very similar to SALAD. It uses object-based image analysis and supervised machine learning to map landslides. It can take any optical imageries, Sentinel-2 or very high resolution optical imagery that are provided by private companies as well. So the difference between SALAD and this is SALAD is available as a standalone code, which is available to public. But what Aladdin has is they have a cloud implementation in European Space Agency's geohazard exploitation platform. So they have both iteration of it online. So Aladdin HR is is what you use if you want to detect landslides using Sentinel-2 or Landsat. And then they also have Aladdin VHR, where you can bring in your own high-resolution commercial imageries and then map landslides using it. So it's a very simple interface where you just provide, if you're working with public imagery, Sentinel-2 or Landsat, you just provide an AOI and choose what imageries you want to make. And since it's an object-based image analysis-based system, you provide some segmentation parameters, and then after processing, it outputs polygons with possible landslides. So So as I said, like the CNRS EOS team also utilized object-based detection methods, so segmentation parameters. So in the screen, it lists what segmentation parameters needs to be set, and you also need to provide some training data, right? So here, like I think they used 4 kilometers square of the imageries and manually mapped 394 landslides to detect landslides. So one difference with Salad here is also like they use a lot of features. Salad I think uses 5 or 6 features, but here you can generate and use up to 60 features, spectral, textural, etc. So as this system utilized a very high resolution imagery from Pleiades, like they were only able to map the Peak Makaya National Park where majority of landslides were present. So to validate these rapid response automatically generated landslide map, we need a reference inventory. So the CNRS EOS team also led an effort where they manually mapped landslides in polygon format, which is very much necessary to validate the automated methods. So here, like they manually mapped about 14,000 landslides, combining Pleiades imagery, Maxar, and Sentinel-2. And this reference inventory might be useful for future research as well. So if you're interested in it, you can download it for free from NASA's cooperative open online landslide repository, Cooler. So in terms of validation using the CNRS EOS reference inventory, we used a two-step approach. The first one was we just calculated accuracy matrices using intersecting landslide polygons between the automated system and the reference inventory that was manually mapped. So as I mentioned before, like we are using two accuracy matrices, producer accuracy and user accuracy. So it basically calculates true positive, false positive, false negatives, and gives you a value, right? So gives you a value. So true positive is basically landslides that were present in both data. False positives are landslides that were mapped by the automated method that were not present in the inventory, and false negatives are landslides that were present in the inventory, it but uh, but those were missing in automated mapping. So producer accuracy, as I said before, gives you an assessment of what percentage of manually mapped landslides were identified, and user accuracy gives you an assessment of what percentage of mapped landslides are actual landslides. So if you look at the table here, like Aladdin had the highest accuracy in terms of producer and user accuracy. HasMapper, like we did validation twice. So HasMapper is the validation was done just to look at ideal scenario of what is actually in the ground. In this case, like their accuracy was 40% for producer accuracy and 27.1% for user accuracy. But like we know that the actual condition of ground is not what is actually depicted in the Sentinel-2 imagery because there were clouds present at the time. So what we did was like we generated a cloud mask out of the Sentinel-2 imagery and masked the reference inventory so that it becomes closer to the actual scenario in the satellite imagery. So once we do that, you see like the producer accuracy jumps to about 60%. So just to get an idea of like how it performs, we plotted false positive, false negative, and true positives, and then just visualize it over the Pikmakaya National Park area. So you saw that Aladdin detects most of the landslides. HasMapper missed a lot of manual landslides. So it's not necessarily because of flaws in the system, but there were a lot of cloud present in the Sentinel-2 imagery when HasMapper system was ran. But over Pikmakaya National Park area, if you see like HasMapper had a lot less false detections. So in a rapid response scenario, like just to have an idea of where majority of landslides were is pretty much important. So what we did was like we generated density maps and try to compare it between the two, the manual and automatically detected landslides. So what we did was like we created a reference grid of 500 meters and calculated percentage area of each grid occupied by landslides, and then try to do a visual comparison here. So for HasMapper, you see like for areas that have greater than 10% 10% coverage, the match is quite accurate, but you do see a lot of areas for HazMapper with 0 to 5% coverage of landslides. So those are all false positives. So in Aladdin, you see a better match, but it also has like higher percentage of false positives as well. So for SAR heat map, like since it produces results as a heat map, it was very difficult to actually validate. So what we did was like we took the CNRS EOS heat maps, CNRS EOS the reference inventory, and then convert it into raster, then convert it into points, and then generate a heat map out of it. So what you see here is like the SAR heat map is very useful for identifying areas with higher landslide density, but it doesn't do a good job identifying areas where there are lesser landslides. And if there are smaller landslides, it doesn't highlight at all. So you see like majority of landslides at Pikmakaya National Park is well captured. But if you look at eastern side where majority of population live, that it didn't highlight any landslides, when in reality there were landslides here. And so based on this accuracy assessment, we can make some suggestions on how to improve this system. So as I said before, like image stacking really helps with reducing noise, and it also helps with landslide detection. So as more Sentinel-1 imageries were available after the event, what we did was like we increased the post-event time frame. So here on the left side, you see landslide detection using only one post-event imagery. So you can see landslide related changes are highlighted. But if you just look at this image, it's very difficult to identify like what is what. And on the right side, you see like we increased the post-event time frame, and the number of post-event imageries here are 80. So once you start going way back from the event, the landslides detection become much more accurate, and you can able to identify or like just say like, hey, those are landslides over here, right? So I guess in future, now currently like out of 2 Sentinel satellites, 1 is down. So generating this heat map is quite challenging. We don't know like when the satellite pass might be happening. So I guess in future, like private companies, we have a lot of private SAR-based companies that are in existence now. So I guess like and they can task their satellites to take imageries with more visits than what a publicly available satellites can. So that might be an avenue to pursue in future. So for HazMapper, you really need to determine a threshold to be able to generate those inventories, right? So determining a threshold is based on user preference. So some people might want to identify majority of landslides with chances of high false positives. Somebody might want to reduce false positives at the risk of missing landslides. So this really depends on the user's preference. One thing to note here as well is like the more post-event imageries that we bring in for the analysis, the more accurate it becomes. So if you compare like landslide detected using 2 weeks of post-event imagery and versus 2 months of post-event imagery, the accuracy was considerably better for 2 month time frame. And to make it a little bit easier to map landslides, I was talking with Corey, and they were talking about future versions of HazMapper to incorporate machine learning based approach as well. So that might be a direction that HazMapper will be heading towards in the future. For Aladdin, I think like it has capability to operate at both post single image mode and by and change detection mode, right? So I think around October timeframe they were able to achieve a pre-event imagery of that area as well, and we just ran some tests on like how change detection is compares to a post-event imagery based detection. So here, like for one, like we were able to separate the 2021 event landslides only, and also like our test highlighted that there was reduction in false positives. So if pre-event imagery is available, I would suggest like using the change detection based method for future rapid response efforts. And so basically, like when comparing this tree system, all of them have their own pros and cons, right? Like for example, the Sentinel-based heat map is capable of identifying areas with a higher landslide density, but it's not capable of identifying areas with lesser or small landslides. HazMapper, utilizing NDVI differencing, identify landslide, but in the process generate lots of false positives. But the advantage of these two systems are that it is available in Google Earth Engine and it's very easy to use. So these can be used at generating first estimate of how the landslide scenario looks after a rapid response effort. And Aladdin, being an object-based image analysis based system, does produce higher accuracy, but it is a little bit time consuming as you need to do some manual mapping to generate the training polygons, and in general object-based processes take time as well. So all systems have their own advantage and disadvantage. Oh yeah, and the manual mapping done by USGS, that's the most accurate method of generating an inventory, but it takes a lot of time as being a manual method. So in terms of like things that can be done in the future, I think like instead of like compounding stakeholders with multiple information regarding the same landslide inventories, we should coordinate and collaborate more. For example, like all the systems that we use for this effort might have been beneficial if we would have been working together. For example, the SAR-based heat map and HazMapper could provide an idea of generally where the landslides are, and then the manually mapped polygons from USGS team can be used to run Aladdin to get more accurate inventories within time. So there must be like some ways for us to collaborate moving forward. Like in perspective of NASA, like after this event, we have always made an effort to get in touch with USGS to see like what kind of response they are doing, and then try to figure out a way moving forward together. And then false positive is the major problem of all these automated methods. So false positive mitigation processes should be prioritized. For optical imagery, we can do slope thresholding. Other things like using land use land cover map and land susceptibility map can also come into play. But to be honest, like there is not a single method using which we can completely eliminate false positives, right? So since we are able to generate these maps quickly, maybe it's worthwhile for us to, as a data provider, to do some manual corrections as well, so that the stakeholders have the most accurate data using which they can make decisions. So, and the final thing to consider is like involving the stakeholders since the beginning on this process, right? For in the process of writing this paper, like we tried to get user feedback on how this data were actually used and if they have any feedbacks, but unfortunately, like we're not able to get any feedbacks from them. I don't know the reason why, we can just speculate, but like incorporating users since the beginning helps them understand like what each system is producing, what are its major drawbacks, and how it can be used in future, right? So I guess like looking into capacity building efforts, because these systems are easily available online, and with a little bit of training, can be easily handled by stakeholders as well. So those might be some of the things that we need to consider moving forward in a rapid response scenario using open source methods. And one of the final thoughts that I want to put forward is like, I think deep learning will be the future in terms of how we do landslide mapping in a rapid response scenario. So deep learning, we just give an imagery to a model, and then it uses mathematical methods like filtering to separate objects in an image, right? So the advantage of this system is like, it's very easy to set up. And as I said before, with object-based image analysis, you need to work with a lot of segmentation parameters. But here, like if you choose a pre-selected tile size on which to train and predict, to train and predict That's the only setup that you need to make. And once you have a trained model, the classification is pretty quick. But the real challenge with this deep learning model is it requires a large amount of training data. So the advantage of like Aladdin or Salad is like you can generate those training data on the fly on a small area for rapid response and then map landslides using that. But for deep learning scenario, it might be a little bit difficult. So having a pre-existing trained model, which has seen landslides from all around the world, is a way to go in the future. For example, here, like for the same Haiti event, I just ran a test out of curiosity. I just took the very high resolution Pleiades imagery and then use a certain portion of that imagery to train a deep learning model and then predicted and just compared the accuracy matrices with what was obtained using OPIA. So here, like the training took a lot of time. It took hours to train that model. But once I had that trained model, like I was able to predict the whole scene that is shown in this image in a matter of one to 2 minutes. So it's pretty quick. So accuracy assessment did highlight that the UNet model had higher accuracy in terms of producers and user accuracy. So I think like this is the avenue to pursue in further. We have seen some efforts from European side where they are starting to experiment or release models which are looking at events worldwide. But I think as a community, we can contribute a lot of inventories and together with the images that was used to generate those inventories to have this global trend model that we can utilize in future pretty quickly. So that's what I'm interested in or working towards right now. So if anybody is interested, you are more than welcome to contact me and we can work together to create this system. So yeah, so at the end, I would just like to thank all the authors who created these models and allowed me to just play around with it and critique it. So if you want further information or are interested about the specific landslide mapping system, you can contact me. I can put you in touch with the developers of the system. Yeah, thank you. And I'm open to any questions.